Would you recognize who this person is?
Surprisingly, this person does not exist. This is an AI-generated face image, or AGFI for short, and is one of the many high-quality generated facial images from advanced generative models available today. In this presentation, I will be discussing my project on the Perceptual Image Quality Score for AI-generated face images. Within the last few years, there has been an exponential increase in generated images. It took humans 149 years to photograph 15 billion images. In comparison, this same milestone was achieved in 1.5 years with AI. But what is a good image? This is determined by our human visual system, what we perceive to be of higher quality with less distortion. To quantify the quality of an image, we perform Image Quality Assessment, or IQA for short. Unlike natural images, we notice that AI-generated images instead possess uncommon distortion. These are uncertain model-specific artifacts such as droplets or unreasonable structures. Let's start by using fine-grained scoring and provide rating ranging from 0 to 5 for AGFIs of varying qualities. This photo looks decent and deserves a moderately high score of 3.45. This photo is perceived to contain multiple issues, deserving a lower score of 2.10. Rating is a subjective IQA, and this process is repeated with multiple observers and images to map our human perceptions of image quality. Eventually, raw ratings from multiple observers are processed by mapping them to a numeric value, which is the mean opinion score, or MOS, to describe image perceptual quality. As can be felt from the toy example, we know that subjective IQA is a tedious process that is both time and resource exhaustive. Therefore, there is a need to automate IQA. This is what I aim to do in my project to achieve objective image quality scores without reference pictures for target AI-generated face images. To meet the goal, my objective is to first develop a novel database for the domain of AI-generated face images. Secondly, I proposed and implemented a new no-reference IQA model for more accurate scoring, a novel, automated solution incorporating transfer learning and image coherency. With the broad objective in place, I defined the scope and narrowed the parameters for my project. To evaluate perceptual quality of images, there is a need to ensure produced score is correlated to MOS. Selected dataset domain is AI-generated face images. Reference database are AG-IQA3K and GF-IQA20K. I set the number of generative models to be an effective testable size of 4, and the baseline of success for my solution can be determined with greater positive correlation using the following 3 correlation metrics. To elaborate on the settings in the methodology of my project, we will examine 3 key stages. Firstly, as no dedicated AGFI IQA database exists, it was necessary to construct a novel database. The database construction involved 4 phases: prompt collection, image generation, subjective assessment, and post-processing. In the first phase, 512 prompts were collected from different sources. To include natural human image prompt, we assessed DiffusionDB, the largest collection of human text input for image generation with stable diffusion models. Raw data was filtered to only select relevant human face image prompt. Thereafter, we supplement the prompts with text prompts from OpenAI, ChatGPT, as well as Google Gemini to achieve 512 unique prompts. To populate our database with AI-generated face images, 4 representative open-source text-to-image generative models were selected. This includes the state-of-the-art model Kandinsky, widely popular Stable Diffusion models, and a highly rated Midjourney model. Subjective assessment was conducted to provide MOS value for quality of text-to-image AI-generated face images. 2 surveys were conducted to annotate images with fine-grained scores for quality and alignment of generated image to text prompt. This is done in accordance with the International Telecommunication Union BT.500-15 standards. Due to resource constraint, a subset of 125 random prompts were selected, and the corresponding 500 images from the 4 generative models were used for the assessment. Lastly, post-processing was performed to obtain the resulting MOS values for alignment and quality. This included z-score outliers removal. Finally, we obtained the AGFI 500 database consisting of 500 unique photos and corresponding quality and alignment MOS value for IQA tasks. To tackle the task of no-reference perceptual image quality scoring for AGFIs, I propose a novel technique termed Generated Phase No-Reference IQA or GEFNIR IQA. To implement the proposed novel NR-IQA solution, I used the following configuration. The architecture diagram of GEFNIR IQA details the usage of transfer learning, image coherency, feature concatenation, and score regression network. A pre-trained ResNet 18 was used as the backbone for feature extraction and score regression. To adapt ResNet 18 to the specific IQA task, its final layer was retrained on AGFI using the Adam optimizer. A deliberate masking is done to selectively highlight or obscure specific region within an image. Through a grayscale mask of pixel value 0 to 255, it is possible to focus on particular areas for obscuration to perform in-painting. The image coherency approach draws inspiration from traditional NR-IQA methods with augmented distortion and the repaint paper, which employs diffusion techniques to enhance image coherency with perceptual quality. In-painting of masked AGFIs were done using repaint trained on the Celeb A HQ dataset. By incorporating the repaint technique into the image coherence approach, it can be observed that AGFI with reasonable and high-quality features are reflected to have greater image coherence with repainted duplicates. This means that in-painted masked AGFIs will output images with higher fidelity to the original reference image. In addition to ResNet 18, BGG16, another prominent neural network architecture pre-trained on ImageNet, was integrated. BGG was selected for its effectiveness in capture similarity score features. BGG16 works to discern image coherency of successfully repainted AGFIs. In the proposed model, feature fusion by concatenation served as a pivotal step in aggregating the multiple sets of extracted features for subsequent quality score prediction. The concatenated feature vector is then fed into 2 fully connected layers, which form the MOS score regression network. The score regression network trained on AGFI 500 learns to map the combined feature vector to a single quality score, representing the predicted perceptual quality of the input AGFI. A benchmark experiment was conducted to evaluate the performance of current no-reference perceptual quality assessment matrix alongside the proposed GEFNIR IQA. The implementation details are as follows. The benchmark experiment was conducted on various perceptual quality NR-IQA metrics, which falls into the following 4 categories: loss function IQA, handcrafted based IQA, support vector regression based IQA, and deep learning based IQA. Under loss function NR-IQA, the metrics selected were inception score, kernel inception distance, and threshold inception distance. Under handcrafted based NR-IQA, the metrics selected were natural image quality evaluator, integrated local NIQE, and blind referenceless image spatial quality evaluator. Under support vector regression-based NR-IQA, blind multi-pseudo-reference images-based measure was implemented to test single AGFIs. Under deep learning-based NR-IQA, the metrics selected were deep bilinear convolutional neural network, contrastive language image pre-training for IQA, and convolutional neural networks for IQA. After predicted scores are obtained from the various NR-IQA metrics, a nonlinear 5-parameter logistic mapping function is required to map the dynamic range of predicted values of different IQA metrics on a common scale. The mapped values are used to tabulate the final benchmark results. To determine the performance of all NR-IQA metrics, including my proposed model, output scores alone are not effective indicators. Instead, correlation coefficients are used to capture the ability of the various NR-IQA metrics in predicting perceptual quality scores of AGFIs accurately, with respect to MOS values obtained in the subjective assessment. Therefore, NR-IQA performance was measured with the following 3 metrics using the newly constructed AGFI 500 database. A higher correlation coefficient value equates to better prediction performance. which means that perceptual image quality scores output can reflect actual human perception more accurately. From the benchmark experiment conducted on the newly established AGFI 500 database, it can be observed that results obtained are comparable to prior study with good generative models. Furthermore, the proposed model, Gefner IQA, trained on AGFI 500, showed impressive results, outperforming existing metrics. Please watch this video, which outlines the entire project.